Hi everyone, the channel Easy Lecture welcomes you. In this series of discussing control system, in our previous class we were discussing about the open loop system and the closed loop system, and also we discussed we given an introduction for the transfer function. As a continuation, in this video we are going to discuss about mechanical translational system, the parameters involved in it, the elements of mechanical translational system, the relationship between the parameters and the mechanical translational and the elements of mechanical translational system. And in the final set we are going to summarize everything, the elements of mechanical translational system, their symbolic representation, the relationship with those parameters, and the Laplace transform of those elements. Okay, so this video is going to be very much useful. Watch till the end. Before entering into the video, subscribe my channel Easy Lecture. Now let us go for the further discussion. So first let us discuss about the parameters involved in mechanical translational system. There are three main parameters which are involved here. They are displacement, velocity and acceleration. These three parameters, we are very much familiar with these three parameters. Displacement, it is a vector representation of distance which is expressed in scalar. So distance is a scalar quantity, whereas displacement is a vector quantity, and the units of both displacement and distance, they are same, meters, right? So difference between scalar and vector, we are very much aware of it. Scalar, it has got only magnitude, whereas vector has got both magnitude and direction. Okay, so here to represent displacement, use this notation x of t, right? The next parameter is velocity. Velocity is the rate of change of displacement. Okay, so whenever we talk about the word, we talk about the term rate of change and rate of change of any parameter. In mathematical expression, it is expressed as that parameter divided by time. Similarly here, velocity, the definition of velocity is it is the rate of change of displacement. So the mathematically it should be written as displacement divided by time. Okay, so here the notation for displacement is x of t, and it has got the unit as meter divided by time. The unit of time is second. So the unit of velocity is meter per second, right? So here when I write velocity in mathematically, I have written it as x of t divided by t, but here in this slide I have mentioned it as d by dt of x of t. Why it is expressed in derivative? The reason is here all the parameters are expressed with respect to time. So time is a continuously varying thing, and when to analyze all these parameters continuously for the entire time period, it may be complex. So it may be somewhat difficult to analyze these parameters, to derive the values of these parameters for the entire time period. So what do? We take a small portion of these parameters, then we analyze that, and then we apply the upper limit and lower limit for the integration to find the value of the parameter, to find the behavior of these parameters for the entire time period, right? So we are to take the small portion, what should we do? We have to go for derivative, or we have to differentiate that particular parameter. For that reason, we have represented these parameters in derivative form. Okay, so d by dt of x of t in meter per second. Similarly, acceleration, it is the rate of change of velocity. When velocity is the rate of change of displacement, acceleration is the rate of change of velocity. So we have to write mathematically acceleration as velocity divided by time, and here also we are going to represent them in derivative form, d square by dt square of x of t in meter per second square. So this is regarding these parameters, and we are very much aware of these parameters. Now let us see what happens when we apply Laplace transform to these parameters. When we apply Laplace transform to displacement, Laplace transform of x of t gives x of s, the thing in s domain, the values in s domain. And regarding the Laplace transform, Fourier transform, Z transform, I have talked a lot in another video titled DSP made simple in single video. You can refer to that video to have an understanding on these transforms, on various transforms. So that will be very much useful. Okay. Next, what happens when next we are going to apply Laplace transform to velocity. Laplace transform of d by dt of x of t equal to s into x of s under zero initial condition. So this we should not forget, under zero initial condition, because we are going to, our main aim is to find the transfer function, and the definition of transfer function is it is the ratio of Laplace transform of output under zero initial condition to the Laplace transform of input under zero initial condition. So under zero initial condition, that condition should not be forgotten. Next, we shall apply the Laplace transform to acceleration. Laplace transform of d square by dt square of x of t is equal to s square into x of s. Again, it is under zero initial condition, right? So with these parameters are over, now we shall talk about the elements. The elements involved in mechanical translational system, there are three elements. They are mass, dashpot and spring. This is the symbolic representation of mass, and this one for dashpot, and this is for spring. Okay, now we shall talk about mass. So every body has its own mass, okay, and we apply force to move that body from one place to another. And how much force do we apply? So whatever the force we apply, there is an opposing force that is developed by the body, okay, and that is based on the mass. If the body is having heavy mass, the opposing force is also heavy. If the body is having lighter mass, the opposing force is also lighter. So that means we have to give heavy force to move a heavier body of heavier mass, and we have to give lesser force to move a body of lesser mass. So this is the thing, right? And before talking about dashpot, we shall talk about this spring. So spring, whenever we give a force to spring, so whenever we give a force, the original position is disturbed, and the spring, it always tends to retain or regain its original position. Okay, again it opposes, it has an opposing force, it develops an opposing force in the form of elasticity. Okay, so this is regarding spring. And the next one is dashpot. So we know what is mass and we know what is spring, and regarding dashpot, we are not much familiar with dashpot. So here dashpot and spring, they work together in real-time applications. So I will give you some illustrations with which you will understand that. So here nowadays in official buildings there are automatic doors. Okay, and in the upper portion of the door there is a structure which is screwed, which is fixed, connecting the door and the wall. Okay, so what happens when we open the door opens, and after that when we release the door, does it close suddenly? Does it move suddenly? No. Spring is there. Due to the spring, it closes, the door closes, but it doesn't close all of a sudden. There is a slow motion, because for safety purpose it should not, if the door shuts suddenly, then there is a chance for the door to get damaged very quickly, right? And if it moves slowly, if it shuts slowly, then it ensures higher safety, right? So how does it occur? It occurs because of this dashpot. So what happens when people open the door, okay, and there is a structure inside the thing which is fixed, and inside the structure there is a gap, and when the door is open, the piston in the gap, it releases, and through the vent the oil, okay, which are the dashpot, which are the viscous fluid or dashpot fluid, they enter into the gap, they fill the gap. Okay, and when the person releases the door, what happened? The piston, they cannot move very quickly, all of a sudden through this gap, because viscous fluid or this dashpot fluid is there. Okay, so they move very slowly, and due to this the door also shuts very slowly. Okay, so here viscous fluid or dashpot fluid, we can compare this with the other examples. For example, when we drop a coin in air, it falls due to gravity very quickly. And when we drop a coin in a container containing water, it moves slowly. Okay, it sways and moves slowly and reach the bottom. It takes much time. Okay, when we drop the same coin in a container containing oil, what happens? It moves further slower and it takes more time than when it was dropped in water. Okay, so here it is giving some kind of friction. That oil, it is giving some kind of friction. Okay, it is opposing the movement of coin. Similarly, this dashpot, it opposes the sudden motion by giving some friction. Okay, so it also develops an opposing force, and the opposing force is due to viscous friction, right? And this is not the only application where dashpot is used. Dashpot is also used in shock absorbers. So in shock absorbers, what happens when the body of the vehicle, to avoid a sudden changes and to provide swinging like of motions, these dashpots are used. So therefore they provide higher safety, right? So this is regarding dashpot, right? Now let us go for further discussion, right? Where we shall talk about the opposing forces due to these different elements. So opposing force due to mass can be written as, so we know mass, the relationship between mass, force and acceleration. Force is equal to mass into acceleration. So we know, we are very familiar with this mathematical formula, Newton's law of motion. Force is equal to mass into acceleration. So whenever we talk about the opposing force due to mass, we can write as opposing force Fm is equal to mass into acceleration. Acceleration in derivative form is m into d square divided by dt square of x of t, and when we apply Laplace transform, it becomes m into s square into x of s in s domain. Similarly, the opposing force due to dashpot. Okay, so opposing force due to dashpot is directly proportional to velocity, and to remove the proportionality, we go for the viscosity Fb equal to b into d by dt of x of t. Okay. Next, the opposing force due to spring. Again, when we talk about dashpot, when we apply Laplace transform, this becomes b into s into x of s, right? Next, opposing force due to spring, and in spring the opposing force is directly proportional to displacement. Okay, so f of k is directly proportional to x of t. X of t is displacement. To remove proportionality, f of k equal to k into x of t. K is elasticity, right? When we apply Laplace transform to this, it becomes k into x of s, right? So now this is the in this slide I have summarized all the things that we have discussed today. These are the components: mass, dashpot and spring, the symbolic representation of all these components. So here I forgot this, it should be drawn like this, two lines on both the sides, and differential equation of these components. So mass is directly proportional to opposing force due to mass is directly proportional to acceleration. Opposing force due to dashpot is directly proportional to velocity. Opposing force due to spring is directly proportional to displacement. And upon applying Laplace transform to this, we get m into s square into x of s for opposing force due to mass. For opposing force due to dashpot, we get b into s into x of s. For opposing force due to spring, we get k into x of s, right? So with this video, we have understood the different components, different parameters involved in mathematical translational system, and the relationship between everything. Okay, in the next slide, in the next video, we will be applying all the knowledge that we gained in this video in solving problems. So watch next video. Till then, bye. And don't forget to subscribe my channel. If you like this video, kindly comment, like, share and subscribe the channel Easy Lecture. Meet you again in another video in which we will be discussing the problems related with this. Thank you. Bye.